it is time. The recorder has started already, so I'm going to get started. And before I get started, I'm going to check one thing because I have my application set up to turn off the ringer. Yep. Okay, that's good. It's based on the calendar. So Tasker is one of those apps you can download and install on Android. I'm not sure about the iPad. But it's really cool because it is quote unquote really programmable. And mine is programmed so that if I mark on my calendar that I have a particular appointment and it's marked as busy, then it will automatically turn off the ringer. So I just have to block off the time for the class, on my calendar, and then it will automatically, silence, during that time. So I think that's pretty cool, because you don't have to program the application itself individually. You just have to put everything into your calendar, and then it will respond to that and turn off the ringer during a meeting or whenever you mark yourself as busy. So that's kind of cool application. I like it. All right. So what we'll do today will be kind of like two things. The first one is to go over the homework assignment just a little bit. Because I assigned it the other day, but didn't get a chance to really talk about it. Well, okay, I take it back. We actually talked about it quite a bit already. It's just that I never really presented, what it looks like in the actual homework assignment. So this is what it looks like in the actual homework assignment. It looks really kind of nasty, like a big blob of equations here, and that's only because I copied and pasted from everything that I did in class on the other day. So this is really nothing new. It's just a copy and paste of what we did the other day. And this part here, all the way up to, but excluding the last line, so everything from here to here is really just dealing with the left-hand side of the conjunction. And then the other part is dealing with the right-hand side of the conjunction. So basically, when we combine the left-hand side and the right-hand side, we come to a conclusion, which is this part here. I know it doesn't show well, but if you have a higher resolution, things won't mash together like this here. But this is where we left off. And what you need to do is to go from here and prove that we can associate Q equals R first, and then we can put P equals to the result of Q and Q equals R, and restructure things like that. Okay, so that's basically what you need to do for your homework assignment, and the way to do it is really kind of reading the proof backwards. Okay, the ones that I have done already. If you read it backwards, that will give you some clue of how to do this, because we have pretty much the same kind of elements. It's just that we are moving things around a little bit and do it in a reverse way. So are there any questions? Has anyone tried to do this? Yep. Is it?
From the destination and go back into the video.
Yeah, you can start with the destination as well, because if you start with the destination, which is this part here, and you apply the same steps that I did earlier, then you will arrive to pretty much the same thing here, and then you just have to rearrange things a little bit based on the commutative law of disjunction and conjunction, and then that's the other way to do it. Yep. In other words, you can work backwards, using the final form, and have both of them to meet midway. Okay, that's basically one way to describe it. So that's your homework assignment. So you might want to spend some time to do it, over the weekend, because this might take you some time. Okay, because if this is the first time you do proofs like this, it might take you some time. Okay, so that's the first part of today's lecture. I'm not going to go too far, with doing this part. And then the second part is your practice exam, which is here. I tried my best to come up with as many different type of questions as possible, but these are the ones that I can come up with during that time. So we'll go over these questions. The more difficult ones are at the bottom, so we'll go over the easy ones real quick, and then we'll get to the difficult ones. The first one is pretty easy. This is like testing your knowledge of what is a set and how to perform the union of different sets. Show the elements of set X assuming it is defined as follows. So we have a singleton, which means a set that only has one element, 1, 5, 7, 0, 1, 5, 4. Okay. So if you take the union of all of these sets here, what do you end up with?
0, 1, 4, 5, 7.
0, 1, 4, 5, 7. That is correct. Now it doesn't have to be in that order, okay? Because ordering within a set is not important. So you can just as easily call it the elements 1, 5, 7, 0, 4. That will work just as well. The bottom line is you cannot have duplicate elements in a set. So you don't want to see 5 twice, and you don't want to see 1 twice either in the set. That's the bottom line. And then the second part of this question, which is what is the cardinality of X? That's easy, right? Because once you know there are exactly 5 elements, 5 is finite, and it's easy to say, okay, the cardinality is just 5. Are there any questions about number 1, question number 1? Okay. Number 2 is a little bit more of an application of what we know about taking the difference of a set. So this one is basically saying, what is the set 1, 2, 3, 4, 5 minus the set 2, 4, 6, 8. Now remember, when we do a subtraction, we are looking at a result that has all the elements in the first one, but excluding elements in the second one. So what would be the end result of this operation? 1, 3, and 5. Yep, it will be the set of elements 1, 3, and 5, because it will contain all the elements in the first set or the set on the left-hand side, excluding elements that are in the second or the right-hand side. All right. Any questions about number 2? Now, only if all questions in the exam are like this. I mean, this is like, wow, that's easy. Number 3, given any 2 sets, A and B, what has to be true about this whole expression here? Okay, A intersect with B intersects with A minus B. That's actually a pretty easy one. Okay, what you need to do is to draw a picture. Okay, so you draw a picture here, you have set A, and then you have set B. In other words, this is set A, and this is set B. I can use like lines here to represent this is the first set, and this is the second set, right? So we want to calculate, or we want to figure out what is A intersect with B. This part here is A intersect with B. So the cross, pattern is basically A intersect with B. Now the question is, what is A minus B in this picture? All the things that are in A, but not in B, right? So the stuff that is in A but not in B is everything that has the horizontal, bars. So A minus B is that part. So when you look at these two, okay, and you say, I want to look at the intersection between these two, what is the intersection? It's an empty set. There's nothing that is intersecting. Are we talking about, are we doing okay so far with this? Because A intersect with B, okay, let me use a different color, that would be better. This is A intersects with B. What about A minus B? A minus B looks like a moon here. Okay. This is this is A minus B. So when you look at the intersection, there's no intersection between these two, which is A intersect with B and A minus B. So the answer is an empty set in this case. Are there any questions about the third question in the practice test? No questions? All right. Moving on to the fourth question. The fourth question is, given that f is a function that maps from some kind of domain D to some kind of codomain E, the cardinality of which 2 sets must be the same? Okay, hold on a second here. How many sets are we talking about when we have a function that maps from a domain to a codomain? We're talking about 3 different sets. Now the 2 that are really obvious are the domain and the codomain. Okay, those 2 are really obvious. But the function itself as a mapping is also a set. It is a set of 2 tuples, picking one element from D and picking one element from E. Right? So that really is our third set. So when I ask this question and ask which 2 must have the same cardinality, which two do you think must have the same cardinality? F and D must have the same cardinality. Now, E can be different. E can be smaller when you have something that is, when F is not injective, okay? You can have E being smaller than D, or you can have E being larger than D, then it is not surjective, because it's not possible to map everything from D to E. Are there any questions about question number 4? Okay. So it is still kind of testing, whether your knowledge of, what is a function and stuff like that, but it's kind of merged with, what we understand about sets, because we are now talking about the cardinality. Question number 5. Describe this function. It is f. It maps from real numbers to real numbers, and the actual definition of f is just, f of x is x squared. In terms of, whether it is surjective, not subjective, surjective, injective, and bijectiveness. Okay, first of all, is this surjective? No. It is not surjective because all negative numbers in the codomain are not mapped to. Okay, so it is not surjective. Is it injective? It is not injective either because 1 and -1, they both map to 1 on the other side. So it is not injective. Well, because it is not surjective and it is not injective, it cannot be bijective. Question number 6. This is really kind of straight out of the text. In propositional calculus, the not symbol is an element of which set? Now, there are 4 different sets to define propositional calculus. There's the alpha, which means it is defining 0, 1, PQRST, psi, phi, and rho, and stuff like that. So it defines all the basic symbols that we use. There's the omega set that defines all the connectives. The connectives include the ones that require 2 items, like conjunction, disjunction, implication, and equivalence. It also includes the ones like negation that only requires 1 thing. So the answer to this question is it belongs to omega. To be more specific, it belongs to omega 1 because omega 1 includes all the connectives that only need 1 item. But if you answer with just omega, it's a perfect answer as well. Okay, because omega 1 is a subset of omega. So if you say it's omega, hey, that's good. Any questions about number 6? Well, while we are at it, let's also look at the other ones. We have alpha, omega. What is iota? What is in the iota set? Things that are, by definition, true. That's right. And then we have the last one, which is sigma. And what do we have in sigma? Those are our no. Well-formed formulas are created by how you kind of mix and match alpha and omega. So what is in a sigma? Transformation rules, okay, or inferences. Okay. So those are the 4 sets. When you talk about a propositional calculus formal system. All right. Question number 7 is the first one that asks you to make a proof. So we'll take a look at this one. Prove the contraposition theorem. The contraposition theorem is basically saying P implies Q is the same thing as saying not Q implies not P. Okay. In other words, these 2 expressions are exactly the same. When one expression is true, the other one has to be true. When one expression is false, the other one has to be false. But how do we prove it? Using only the axioms that we have talked about so far. Okay. So we'll go take a look at the axioms first, okay, because we want to make sure that we do not use anything other than the axioms that are already on the list. So the list of axioms is here, so you can just go ahead and click it if you want to. And in the test, I will give you a reference, so you don't have to print it and bring it with you, just in case some people forget to do it. Okay, so these are the axioms, and what we want to do is to prove this part here. Okay, so we'll go ahead and get started with this is what is given. Now, if that is what is given, you only have so many things that you can apply right now, because according to most of the axioms, most of these do not deal with implication. Okay, so when you look through these three, they don't mention implication whatsoever. You look at these two, no implication, no implication, no implication, no implication. And finally, we have a implication. Okay, great, let's start with that one. Okay, so if you start with this one, P implies Q is the same thing as not P or Q using axiom 1.8. And this is also a good time to thank Vincent for his modded MathJack previewer, which is here. It's just, you know, this is the whole previewer. So what I'll do is I'm gonna do the same stuff as before. Begin, align. This basically sets up the environment to display multiple lines of equations and make everything line up. Okay, so what we have to begin with is P implies Q. That's what we are starting out of with. And using axiom 1.8, I think, so let's see, it is 1.8. We know that this is really saying the same thing as the negation of P or Q without any negation. And we'll use the tag ability to say this is from axiom 1.8. And double backslash means, you know, open a new line. So now, you know, in the equation area, it will open up a new line as well. And I'll go ahead and magnify a little bit, and everything actually magnifies pretty well too. That's good.
It's all CSS stuff.
It's all CSS?
Yeah, really.
Okay. All right. Now that we have the negation of P or Q, now we can do something about that. Now, here, this is the trouble, this is the problem of proving. Because at this point, there are many axioms that can apply. So you have to kind of think about, okay, but which one do I want to apply? Sometimes it helps to start with a destination or where you want to end up at and say, okay, can we work backwards from there? Okay, because if you try to work backwards, then you will say, hey, we somehow have to get to not Q, and then we have to somehow end up with not P. But not P is here already. So now the question is, where is that not Q coming from? We have to introduce negation somehow. Okay, and then you go through the axioms and you ask, but how do I introduce negation? In other words, how do we start with something that has no negation and now end up with, you know, actually some of the negations on top of that? And that would be double negation, and it is right here, which is 1.5. In other words, when you look at axiom 1.5, which is this part here, it says every time you have any expression P, it is always the same thing as the negation of the same thing, which sounds really silly, right? I mean, it's like, okay, why do we want to make it more complicated? But this is one way to introduce a negation when there's none to begin with. Well, it introduces a pair of negation. But it's okay. We'll go ahead and see where this can lead to. And this is the nice thing about the aligned environment is, you know, you can basically line up all the comparison symbols, all the relational symbols can line up automatically. So we'll go ahead and keep not P just the way it is, but Q will say it is the negation and the negation of Q. And this is using axiom 1.1 again? I cannot remember the numbers. 1.5. Okay, there we go. All right. So are there any questions at this point about, you know, which axiom I applied in order to end up with not Q from Q?
No problem.
No problem? That's okay? All right. So the next thing we'll do is to say, well, the end result is not Q implies not P. So maybe if we exchange the positions of these two, you know, within the disjunction, it'll make things easier to see. Okay, seems to make sense. If not, you know, it's not going to be a bad move because it doesn't really do much. It's just exchanging the positions. So we'll go ahead and do that. So we'll just be moving the negation and the negation of Q onto the left-hand side and move not P to the right-hand side. And this is the commutative law of disjunction. So we'll call that 1.1b because it's only for the disjunction. So we'll tag it as 1.1b, like that. Okay. Now I can use the associativity of negation and say, well, it doesn't really have any rules of associativity because it only takes one single operand. So you have to apply the inner negation first and then apply the outer negation. In other words, the introduction of parentheses is completely redundant. But it does make things a little bit easier to see, so I'm going to do that. So I would say this is the negation of Q, or the negation of P, and in this case there's no axiom to quote because we are just introducing extra parentheses to clarify the ordering of operations. But is this giving you some idea of, hey, this looks like a certain pattern? Compare this line with the first one, okay? The first one looks like a negation of something or something. This one is now also looking like the negation of something or something, right? It's matching that pattern. Now, every time you see something that has this pattern of not something or something else, you can go back to the axiom, go to axiom 1.8 and say, hey, if I see this, I can reverse it back to this side. In other words, every time you see the negation of something or something else, you can say it is. Another way to say that is something implies something else. Okay, well, that can be helpful in this case because now I can finally group things together and say this is the same thing as the negation of Q, which is what is the negation of Q is what is being negated on the left-hand side of the disjunction, and then this is the implication, and the other side is really just not P. Just like that. So now we have our answer. Are we doing okay so far with this one? And I have to tag it with axiom 1.8, but this is going in the opposite direction. So this is tag axiom 1.8 again. That's the conclusion of our proof. Technically speaking, I have to put a QED here, just to say, okay, this is the end of the whole proof. Are there any questions about this proof? No questions? Okay.
So if we get partial, if we get part way through, will you give us part?
It depends on whether your part way is in the right direction, because you can spend a lot of time doing derivations that actually do not lead to the right direction. So that depends on whether you hit the, I would just call it landmark, intermediate results. So if it takes you like 5 derivations, but eventually got here, then I'll give you partial credit for that part. If it takes another 20 derivations, but eventually get here, then I'll give you partial credit for that. Is that making any sense? Okay. Because the difficulty of grading something like this is you can be doing a lot of derivations, but it doesn't really go to it's not going in the right direction. How many people still remember how I compare, how I describe, a proof like this? In other words, without the proof, okay, now without a proof like this, starting with a statement or an expression like this and a result like this one here, is this always there or is it there only because of the proof? It has always been there, right? So the process of proving is really finding a path to go from one well-formed formula to where we want to go. Is that okay? So it's kind of like finding treasure. In other words, you start from here. This is already gone, and we need to put all these away so we don't accidentally use these. So basically, it's basically the same thing as you're starting from here, and this is your destination already. In other words, this is our P implies Q, and this is not Q implies not P. it's already here, has always existed because of the system of logic. But the steps of the proof is really just connecting, these steps here, so that we can go from here to here, here to here, here to here, here to here, and then finally we get to the destination. But if you start from here, you can also go in the wrong direction that has nothing to do with the proof itself. And maybe eventually you get to one of the steps. Okay, so I cannot give any partial credit until you get to one of these, intermediate steps. Is that okay? All right. I like how I, just made a path around the Greek symbols for propositional calculus. All right. Is that okay so far? Okay. All right, so let's get back to the questions, and we'll get to question number 8. Question number 8, to some people, it is actually easier, because this time I want to use a truth table to prove the contraposition theorem. Now, a truth table is a whole lot easier to work with, but in this case, you kind of have to work with the individual items first, and then tell me, why the table or why the two columns are the same. So when you use a truth table, it's easier to probably just draw it on the whiteboard. So what you need to do is to say we have two independent variables p and q. We have one expression p implies q, and then we also have the other expression which is not p. It's not q implies not p. Okay. With p and q, those are independent, so we have 4 possible combinations. P implies Q is by definition, a certain way. So by definition, false implies whatever is true. Okay? So these two are true to begin with. This is the only one that is false, and then the last one is true as well. Now, but you cannot just say, oh, this is 1101 as well, and I'm done. Okay? Because that would just be kind of trivial. So what you need to do in this case is to spell out what is not Q first. So not Q is the negation of Q here. So this would be 1, 0, 1, 0. Not P is the negation of the first column. So this will make it 1, 1, 0, 0. Now knowing that this is 1, 0, 1, 0, this is 1, 1, 0, 0, then you can work with the implication. In other words, separate into 3 columns here. So now we have not Q implies not P. True implies true is true. False implies whatever is always true. And that applies to this one as well. True implies false is false. Then you can make the conclusion and say, hey, look at this column. It is exactly the same as this column here. And that's the proof that these two are the same because they have exactly the same outcome. Are there any questions about number 8? Yep.
Why does truth imply false? Is false.
True implies false is false because the implication itself is, that basically is how it is defined. Remember the analogy that I was using, like you pay me $50 and I tell you if the sky is purple, you will pass this class with an A.
Yeah.
So if the sky is actually purple, and I say, you know what, I don't feel like passing you this semester, then you're going to get you want to argue, right? But Tech, you said da 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 da. That made what I said earlier. That made me break my promise. So the statement was actually false. Does that make any sense? But that also kind of explains why on a sunny day when the sky is blue, I can do whatever I want, and you still cannot get your money back. Because the statement that says, if the sky is purple, blah, 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 has nothing to do with what happens, on the day when the sky is blue. Okay? Because most people actually have more problems with that than anything else. Is what if, for the first 2 rows, okay, if the sky is actually blue, when my statement has to do with when the sky is purple, how come these two, is still true? It's because you cannot prove me wrong. Right. So we are kind of like just blazing through the first 8 questions, more or less. And now we get to question number 9. Question number 9 is not really nasty, but it's just, it requires a few more steps and a little bit more thinking. So we'll consider the following definitions, and this has to do with relations. R1 is a relation over integers, and it has to do with less than or equal to. Okay, less than or equal to, typically written as this. Okay. R2 is pretty much the same thing, except it is representing greater than or equal to, which is represented as that usually. So when you look at relations, each one is a set. Okay, so you have the first thing you have to remember is a relation is a set. It is a set of tuples, in this case 2 tuples of integers. The first thing, okay? In fact, what you might want to do, okay, I'm thinking about whether to use the whiteboard or to use the overhead projector. I'll just go ahead and use the projector here. Okay. So is it okay to erase this part?
Yes.
Okay. So, and then let it double check and make sure the recorder is still on. Yep, it's still there. And it is recording my voice as well. Okay, just double checking because sometimes I make mistakes. Okay, so in this case, R1 is actually a set. Now it is a set of infinite number of elements, so I cannot enumerate everything here, but I can give you some idea of what is here. 0, 0 is here. Because 0 is less than or equal to 0 is a relation, right? I mean, it does hold. The relation holds in when you're dealing with integers and also real numbers. 0, 1 is here as well, because remember r_1 or r subscript 1 is less than or equal to. 0 is less than or equal to 1, so that's why it's here as well. And you can see that there will be like many other elements here. The other one, which is r_2, r subscript 2, is greater than or equal to. And I probably should not be using a line. Well, I could, but I'd have to make it a line like that. There we go. So when we're dealing with R2, it is greater than or equal to. So that means 0, 0 will still be here because 0 is greater than or equal to 0. But in this case, 1, 0 will be here because 1 is greater than or equal to 0, and so on. Is that okay so far? So this is the first thing you have to remember is a relation is a set. A function is a set. And that's why we talk about set theory first, before we talk about both of these concepts. Is that okay? So when you go back to the question, it's saying, let's do something about these two sets. So let's go back to the question, which is here. So the question is, first, state the properties of R1 and R2. They're kind of the same, okay? They're in opposite directions, but they're kind of the same. So I want to know whether they are reflexive or not, okay? I want to know whether they are symmetric or not. I want to know whether they're transitive or not. And once you know these three, you will come to the conclusion of whether they're equivalent or not. Because in order for a relation to be equivalent, it has to be true for all these three to begin with. Okay? All right, so let's see how well you remember what is being reflexive. What is reflexive as a relation? What makes a relation reflexive over a particular set?
Reversible. Reversible.
You have to see yourself, okay? So the name reflexive, implies that you have to see yourself. So that means, 0, 0, 1, 1, 2, 2, over all integers has to be in a relation. So it's less than or equal to reflexive. It is, okay? Is it symmetric? Now, symmetric means, if ARB is a relation, then BRA also has to be a relation. Nope, it's not symmetric. Is it transitive? In other words, if ARB and BRC, then it implies ARC. Not here ARC, but a relation C. Okay? Almost got you. So, is R1 less than or equal to transitive? It is. And so is greater than or equal to. So in both cases, in both R1 and R2 in this case, they are both reflexive, and they're also both transitive, but neither is symmetric, which also means neither is equivalent. Are we doing okay so far? Okay. And this is also a good time to remind you guys, it is open book and open notes. So that means you can print out or handwrite anything you want prior to the test, bring it with you to help you out in the test. But it's a no electronic kind of test, so you cannot bring an iPad or a laptop computer. It has to be printed or handwritten. Okay? But that gives you time, right? Because the test is next Thursday, so you have 1 week to prepare for the test. So as you study, you might want to jot down the notes on the side to make a more concise version of my notes. Now, not to say that you should not bring my notes or a textbook. If you find a good textbook on the subject matter, go ahead and bring it with you. Okay? But it's really helpful when you can condense everything onto just 1 or 2 sheets of paper. It's much easier to go over those things and find what you need to find. And also the fact that you're preparing for you're writing and compiling your own cheat sheet, that by itself is studying already. When I was in college, that's a long time ago, when iPads did not exist, usually I would be, the professor sometimes allow like 1 sheet or 2 sheets of paper, as a cheat sheet, and that's it. No book, nothing. And by studying and getting ready, to compile my own cheat sheet, most of the time, by the time I get to the exam, I did not even need the cheat sheet itself, because by preparing the cheat sheet, I have everything already, memorized. But that just kind of worked for me. I don't know whether it works for everybody or not. All right, now here comes the fun part, okay? Here comes the fun part, because now I'm taking the intersection of the 2 relations. In other words, R1 is really just a set, right? It's a set of two tuples, and R2 is also a set of 2 tuples. Nobody says that these 2 cannot be, I cannot use the intersection operator on these 2 sets, right? So the question now is, if I do an intersection of these 2 relations, what do I end up with? That's the question, and that's why, here is the actual question. Is there a more common name of this relation R3 referring to R3? What do you think it is? It's just equal to. It's just equality. Yep. So the name is equality. So this part you have to say yes, there's a more common name, and then you say equality over here. And now that we know this is equality, what about the properties of equality as a relation? Is it reflexive? Yes. Absolutely. Is it symmetric? Yes. Yep. Is it transitive? Yes. Then it is equivalent. Yep. So that's basically what this is asking. And you can also see that this by the type of question, it also has partial credit. In other words, you can answer some of these questions correctly, and if you don't get everything correct, you will still be able to get partial credit. Are there any questions about number 9? No questions about number 9? Okay. Let's take a look at number 10. Number 10 is actually longer too. Okay, number 10 is asking you to think about the cardinality of natural numbers, which is known as aleph 0. Recall that we can fold integers to map to natural numbers using this particular way. How many people still have some recollection of this stuff here? Okay, so what we're really doing is, when you look at integers, it goes in both directions, right? This is 0, and it goes in both directions. When you look at natural numbers, it goes in only one direction. So the question now is, how do we map integers into natural numbers? And the way we do it is simply to say, okay, for all the non-negative numbers, we'll map it to even numbers over here. So 1 maps to 2, 2 maps to 4, and so on. Then we are leaving all the odd numbers in the natural numbers. Those are for the negative value. So negative 1 maps to the first odd number, which is 1. Negative 2 maps to the second odd number, which is 3, and so on. So by doing it this way, I can map any integer into a particular natural number, and it is a one-to-one correspondence. Are we doing okay so far? This is just a review of something that we have talked about. All right, so that's the first part. The first part is to state that we can map integers into natural numbers, and it is a one-to-one or bijective function to do it this way. The second part is to say, if I give you a two-dimensional natural number coordinate system, I can also map it into just natural numbers using a southeast to northwest scan count direction. Okay, let me explain what that means. What that means, it really shows better on the whiteboard. So what it means is like this. Okay, so if you write out your x-axis and your y-axis this way, and this is 0, 1, 2, 3, 4. I'm not even going to go that high. So this is 1, 2, 3, 4. I'm going to sweep in this direction. So the direction I'm sweeping is from, this is my southeast to my northwest. Okay? So I start with 0. Okay? So 0, 0, which is this point here, is associated with 0 itself. So this is the first item of the function. Are we doing okay so far? So I'm looking at the mapping here. So this mapping is G. Actually, this G is a set of these correspondence. And then the next one is here. Okay, this is 1, 0. Got it wrong. I got the x and the y reversed on the projector. I got the x and the y reversed, so I'm actually scanning in the opposite direction. So I'm mapping this one to number 1. I'll just be consistent with what I have on the whiteboard here. So this one is mapped to 1, and then this one is mapped to 2. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and so on. So by doing this type of traversal, I can map anything on a 2D plane like this, as long as it is just using the integer to natural numbers. Is that it?
Sorry, can you share the mapping again? We can't see anything from this side.
Okay. Maybe it is better off if I use a spreadsheet. That's it. This is even better. Wrong class. Okay, so we'll go ahead and do it like this. So we have 0, 1, 2, 3, 4, and then we have 0, 1, 2, 3, 4. And what I'm doing here is I'm mapping this cell. Okay, maybe it shows better if I do it this way. So hold on a second, this is much better. Okay, there we go. Okay, so I will also mark here. I'm going to highlight these, in a different way, just so that you know this is just the coordinates of stuff. There we go. Okay, so this is the actual natural number corresponding to that position. The intention is to go from here. This is my 1, 2, and then 3, 4, 5, 6, 7, 8, 9, and then this would be 10, 11, 12, 13, 14, and so on. That's the intention, but I got it wrong in the actual question. I went in the opposite direction, but that's the intention. But the point is, it is just going diagonally, and then you move on to the next diagonal line. Yep.
So the way this looks, so like the two tuple 0, 0 would map to 0.
Correct.
And then the two tuple 1, 0 would map to 1, and so on.
Yep, exactly. So this 7 is actually corresponding to 2, 1. Right. And this 13 is mapping to 1, 3. But you can see, I can extend out the x and the y axes indefinitely, and if I keep sweeping this way, every single cell is going to have a unique natural number associated with it. So that means, you can give me a two-dimensional space of natural numbers, and I will still be able to map that two-dimensional space to just natural numbers. Is that okay? All right. So, but there is significance to this whole thing. The significance to this whole thing is this part here. Because now we have a way, it is a one-to-one correspondence. Now the one-to-one correspondence, which means it is bijective, is not, I'm not going to prove it, but you can just kind of see it. Because if you look at this picture here, and you just say, okay, the x-axis goes into infinity, the y-axis goes to infinity, and I keep doing this indefinitely, you can see that every single cell is going to have a natural number, right? That makes it injective. On the other hand, if you pick a particular natural number, it will have a place onto this two-dimensional space, and as a result, it will end up with a x-coordinate and also a y-coordinate. That makes it surjective. Since it is both injective and surjective, it is bijective. Now, if it is a bijective function, then I have now just proven the cardinality of any, first of all, the cardinality of something like this, which is the Cartesian product of natural number with natural number, is the same thing as the cardinality of just natural numbers, because it is a bijective function mapping from the domain to the codomain. I can extend this particular method so I can deal with not only a plane, which is two-dimensional, but I can extend it to three-dimensional, four-dimensional, and so on. And which means if you give me a fixed number of dimensions, n, lowercase n in this case, I can map the coordinate system of that space to just natural numbers, which ends up with the same cardinality, which is aleph 0. Yep. Are we doing okay so far with this stuff here? No one seems to be amazed or wow, that's so cool. I mean, when I looked at this, I was going like, wow, that was so cool. Because, if you think about it, it's not really natural, right? Because, when you have integers folding it onto natural number, yeah, that one is kind of, okay, that's a neat trick. But when you look at two-dimensional space and mapping into a linear space, it's like, wow, that's kind of really cool. But it extends to any dimension as well.
Maybe if we had the insight into why it's so cool.
Because everything is now just one line. The conventional sense of using three numbers to represent a position in 3D space can now be folded into one single value, a single integer, a single natural number, not even integer. And that, I think, is really kind of cool. Okay, think about 3D printing. Okay, 3D printing, kind of popular, people are doing it all the time, and you can buy a 3D printer for, can I talk about it in this class? No? Okay, they used to be pretty expensive, and you have to put it together, only to find out that you're missing a few parts, and then you have to have someone to 3D print that part for you in order to put it into your own 3D printer. Okay? But these days, you can buy one for $1,000. Now, I know $1,000 seems like a lot of money, but you can also buy a smaller one for $500, and it's already done. It's pre-made. Open the box, plug it in, put in your favorite spool of plastic, and start printing stuff.
Do you own one?
No, but I'm looking into it.
You can buy the kits for $300 that come with all the parts. So
Okay.
just use the kit.
So there you go. You guys are prompting me to go to Amazon.com to take a look at
3D printers.
3D printer, and this is the one that is $500. It's not big, you cannot really do a whole lot of big stuff here.
Is that the one that does the 7x7 or whatever?
Yep, 8 by 8 by 8 basically. 7.8 inches cube, which is still pretty good size. I mean, my hand, this is about 8 inches. So it's basically a cube like this big. That still includes a lot of stuff that you can do. I mean, you can 3D print a lot of things. But if you think about it, and I'm trying to map it back into what we are talking about. So when you think about this, every single point of whatever you're making, we normally see as a coordinate, right? So many millimeters, or micrometer, or whatever unit you want to use, this way, and how many millimeters this way, and how many millimeters this way. But using the way we just talked about, we can fold everything into a single natural number. Now, is it easy to look at that one single natural number and figure out which point we are talking about in 3D space? No, not really, but it is possible. Yep.
You can use the natural numbers to represent the 3D point itself. Like, if you know if whatever runs that knows the conversion.
Right. And the other nice part is, what if you're dealing with a system and you're running out of integer width, right? Okay. So think about that for a moment.
You can use.
If you use 8-bit integers, okay, and 3D printing, your resolution is not so good, right? Because 8 bits only gives you 256 by 256 by 256. But if you use the 3 number, or the axis, way of representing a point in 3D space, so using this, you're talking about a 3-byte thing to specify one coordinate. And when you run out of resolution and you say, oh, 8-bit is not enough, you move on to 16-bit, okay? So now you have 16-bit here, which is quite a lot, because you have 65,536 points in each dimension. So, but the representation is now different. Okay, even if you want to refer to the same point, the bit pattern representing that one point in 3D space is no longer the same. Now, next, let's say you're dealing with a really, really big 3D printer, so you can 3D print an actual airplane or something like that. That would be kind of cool. Then you find out that, hey, 16-bit is not enough for that. Now we need 32-bit, okay? So once again, the representation is now a lot longer, and when you look at just the sequence of bits within this representation, to represent the same point is no longer the same, okay? Which means whatever file format that you have to use, whatever protocol that you have to use, is now it's sensitive to the resolution. Is that making any sense? Okay. On the other hand, when you look at how we can fold 3D space when we're dealing with only integers into just natural numbers, if a particular point in 3D space is always the same number, and it can always be represented by the same bit pattern. Is that making any sense? More or less. Okay, so it does have that advantage of not being resolution dependent or sensitive. Now I want to find out what is the resolution of this thing. Let's take a look. Okay, I'll just do a quick search here. Resolution. It's 100 to 400 microns. One micron is 1,000th of a millimeter, so it's about half a millimeter. So if you use a mechanical pencil and it's a half millimeter type, that's the resolution of the 3D printer, which is not too bad. I mean, it's not really terrific, but it's not too bad. Yep.
So if I printed like a completely like a cube or something like that, so there'd be like half a centimeter like indentations maybe within the cube. Is that what you mean by resolution?
Right. The contours, will be kind of rough, and it will be within. It's going to be at the most, half millimeter, because it's 400, which is less than half a millimeter.
Gotcha. So like
the steps, basically, that's the step from one layer to the next, and also within the layer, that's how the patterns will look like.
Oh, so even like within the same plane, but actually be able to get that perfectly
I think
clean?
so, because it doesn't specify whether this is just the Z resolution or whether this is just the XY resolution. So I think it applies to all three.
That's
the
pretty
XY,
amazing, actually.
sorry?
That's pretty amazing. Like how good
It's
the
still pretty
resolution is.
useful. I mean, you can still use it to print, some kind of cool stuff. Yep.
Okay.
So I'm not sure whether you guys are, yeah, go ahead.
I heard there was a thing where it was 3D printing like guns or weapons, and they had to restrict some of the models that were online just because there was getting access to weapons.
Well, if that's what they're worried about, then they have to shut down, Home Depot. I can just go through a few aisles in Home Depot and then come up with something that will be illegal. It's just, if you bring that thing around, you will need a bigger vehicle to, take it with you. So I guess, that's the reason why it's not going to be a big problem. It's not concealable, let's just say. But I can understand what you're saying. The material they can use for 3D printing is still very limited. Like what type of material can be 3D printed. The problem is you can 3D print a mold. Okay, you can 3D print a mold, and by doing, I cannot remember the name, but it's a deletive process. But using that, you can use a mold to actually make things that are a lot more durable. Yep. Well, you still need a projectile, right?
Yeah.
But then, when you look at the city code or the county code, a slingshot is counted as a firearm too. So they got it already, well covered. And in the entire state of California, regardless of county, you cannot use a blowgun or own a blowgun. So next time you pick up a straw to drink something, just be careful there are no your FBI agents around you, because they can say, if you're not sucking, with a straw, then they can say, hey, you have a blowgun here, we're going to arrest you. This is a federal crime. Well, state, not federal, but yep. All right, so getting back to this stuff here. All right, so the question now is, there are several questions. Combining all of this, we can now map any integer coordinate system to natural numbers, because we have a way to map integers into natural numbers, and then we have a way to map any dimension of natural numbers to just natural numbers. So that means we have a way to map integer coordinate systems to just natural numbers. Using the way we map integers to natural numbers and the way we map 2D natural number coordinates to natural numbers, what is the natural number corresponding to the coordinate 1, -1? Okay, that's the question. All right, so there are two steps to this process. The first one to this process is the linear portion. So the linear portion is basically saying this is 0, this is 1, 2, 3, 4, okay, -1, -2. This, I don't have to go very far. For natural numbers, 0 is 0, 1 is mapped from -1, 2 is just +1, 3 is -2, 4 is regular 2, and so on. And that's enough. Is that okay? That's the first step. So since we are dealing with 1, -1, so when we convert 1, -1 to just natural numbers, it becomes, the 1 becomes a 2, and the -1 becomes a 3. No, -1 becomes a 1. Are we doing okay so far with that conversion? It's from integers to natural numbers. And we have to do it twice, first to the x coordinate, and then next another time to the y coordinate.
So now we have the x.
Right, now we look this up in the picture that we drew on the spreadsheet earlier and say, okay, where is 2, 1? So 2 is this column, and 1 is over here. So that makes, 7 is the natural number corresponding to the original coordinate of 1, -1. Is that okay? All right.
So, just to make sure I get this straight, that's an xy coordinate system of natural numbers.
Correct.
And then each one of the integers triangle at this point, or in that quadrant,
Yeah, I can keep scanning like this,
Yeah.
you know, yeah,
is a natural number, a mapping location.
correct. Yep,
Just want to make sure I understand.
yep. So this location, this 7, which is a natural number, can map to, you know, 1 comma negative 1 as a coordinate. Are there any questions about this one? Yep.
When mapping the real numbers to natural numbers, do you always start off with -1 first?
Well, this is obviously not the only way to map it, because you can slide, you can slide one line, any way you want to. It will still be a perfect mapping. But, in this class, I always map it this way. 0 to 0, 1 to 2, 2 to 4, and then -1 to 1, -2 to 3, and so on. It will be given in the test, which way I'm doing the mapping.
Okay.
So, this is, basically what I'm talking about. Yeah, in class, we use exactly the same way to map it, and I gave you guys a semi-closed form, because I call it semi-closed because it depends on whether the number itself is positive or whether it's negative or non-negative. But there is a closed form to do this. All right, any other questions? Question number 11. All right, let's move on. So, to show the steps, this is basically me trying to give you guys partial credit, just in case you don't get everything right the first time. So 1 is mapped to 2, -1 maps to 1. So if you can at least get these 2 parts done, you get some partial credit. XY maps to 7, because that's where we find the coordinate. Oops, wrong sheet here. This is why we find 7. So I try to make it stepwise, and you guys can fill in the blanks as you work to the final answer. All right. Any other questions about number 10? Okay. If there are no questions, you might probably think that it's a good idea to work out that system. Just bring yourself a little map or a little lookup table. Okay. Enough said.
AKA, bring it already done.
Well, bring it. Just working on it is already going to be a little bit helpful. I forgot my note sheet. So it's okay.
That's fine.
Question number 11. This is the last one. What we understand is a binary number is merely a representation of a value using base 2. Okay. Now this is kind of important, because a lot of times we tie in the representation of a value with the value a little bit too much. Okay. What is 5? 5 is nothing more than a word in English, and it is F-I-V-E. Okay. But what is it representing? Well, what it represents is this, right? This is a quantity. F-I-V-E is a word. And the reason why we have that word is so that we can talk to other people. How much do I owe you? $5. Okay? $5. Okay? So that's why we have 5. But you know what? This is also known as 101 in base 2. It is also known as 12 in base 3. It is also known as 11 in base 4, and so on. Is that making any sense so far? So this is a quantity, but it has many names. And those names depends on which base we are talking about. And obviously all different languages, natural languages, also would call the same quantity in different ways. So that's why I started off with this statement here, which is basically saying a binary number is just a representation of a value using base 2. As such, there's a mapping, which is a function, from the Cartesian product of 0, 1 as a set to those values. So we'll go ahead and take a 4-bit integer as an example. And this is a function. Okay? Function f is a mapping. It maps from the Cartesian product of 0, 1 4 times. So this means we are making the Cartesian products of 0, 1 with 0, 1 with 0, 1 with 0, 1. Okay? That's the 4-time Cartesian product of 0, 1. And we are mapping the Cartesian product to the actual values. going from -8 to +7. Why do I pick -8 to +7? We're dealing with 4 bits here. That's how signed numbers are represented. Okay? So the most common way to map this is as follows. So 1000 as a bit pattern maps to -8 as a value. 1001 as a bit pattern maps to -7. 1111 as a bit pattern maps to -1. 10000 maps to the value 0, and so on. Okay, and the last one is 0111 maps to 7. Are we still doing okay so far with the representation in binary? Okay, by this time, because you should have taken 430 already, and therefore 360 as a result, how many people have some exposure to the representation of values using bit patterns? But that's basically how things are. But even without any prior exposure to how values are represented using binary numbers, I can now also express this in a closed form, which is basically saying, give me a 4 tuple of zeros and ones. And that 4 tuple is now ABCD. I'm just using ABCD to represent each position of the 4 tuple of zeros and ones. The value that it is mapping to is D times 1 plus C times 2 plus B times 4 minus A times 8. See if it works. Okay, let's give it a try. Let's take a look at 0101. Okay, so when you look at 0101 and you plug into that equation, this is A, B, C, D. Okay, we have D times 1, which means we have a single 1 here. We have C times 2, that's a 0 because we have 0 passed to C as a parameter. B is 1, but that's to specify how many 4s we have. We have 1 of those. And A is -8, but we have none of those, so it is just 4 plus 1, which is 5. Is that okay? What about the bit pattern of, just pick another space here, 1100 in binary? This is A, B, C, D. Okay. We have no 1s here, no 2s, 1 4, and we have 1 -8. So this bit pattern is actually representing -4. Okay. So that's how we map individual digits of a binary number into the value that it represents. And this is by far the most common way to map binary digits into the value that is represented. Are there any questions about the definition of this function? Okay. If I were to ask you to prove that this function is injective and surjective, how would you go about doing this? Of all the techniques that we have used up to this point, which technique would you use which is going to be like, this for sure will do it. There's no way this will fail. It's tedious, but it won't fail. Okay, look at ABCD. Yep, go ahead. Exactly. Use a truth, quote unquote, truth table. Because A can only be what? 0 or 1. B can only be 0 or 1. C can only be 0 or 1. D can only be 0 or 1. So I'm not talking about all natural numbers. We are not talking about all integers. We're just talking about zeros and ones. So this will take some time because it will give you a table of 16 rows. But of the table of 16 rows, you can work out the math using the closed form. And then you can look at the whole table and say, okay, is this injective? In other words, if I have a different bit pattern, does it always guarantee to map to different values? When you look at the actual resulting values, they're all different. So that is automatically guaranteeing it is injective. Yep.
What is closed form again?
A closed form is kind of like this, which is basically, it's a closed form equation. I do not have to spell out each and every single case is a general description that will describe the function itself instead of using, this is not a closed form. This is just basically, enumerating all the, mapping.
Gotcha.
Yep. Okay, so now that I have answered my own question, which is it injective? Yes, it is. Is it surjective? Yes, it is. Is it bijective? Yes, it is. And if you guys want to make it, you can say obviously too. Now, if it is bijective, what is the inverse function? Now, the inverse function is easy to express because you can just give me the enumerated version of everything, right? You can say, 15 maps to, not 15 is not mapped. You can say 7 maps to 0, 1, 1, 1, and just reverse everything. But I don't want you to give me, just the reverse of everything. I want you to give me the closed form of that. So the closed form in this case is going to be a little bit funky because the other side is a 4 tuple. So what you need to do is to give me something kind of like this. This one is obviously incorrect, but you have to give me a 4 tuple on the other side that depends on one single value, which is x here, and that will be the inverse function. And I explicitly said here you cannot use bitwise operators because that's kind of like circular reasoning. Okay, so how would you do that? Now you can utilize any operators in math or C++, which means the ternary operator is at your disposal as well. If the ternary operator is at your disposal, how would you express, the bits, A, B, C, and D? Well, let's take a look. So I'm going to use mouse pad here. So what we're looking for is the inverse function of f applied to a value x. Now in this case, the inverse function has the domain and the codomain already predefined. It has to do with how f itself is already defined, so we can basically use the codomain as the domain and the domain as the codomain because they're just basically flipped. So in this case, the domain is the values from -8 all the way to 7 and only in the integers. So I'm going to use the curly braces here. And the codomain would consist of the 4 tuples going from 0, 0, 0, 0 all the way to 1, 1, 1, 1. All right, so what I need to do is to figure out how do I express the 4 bits given x. And x has to be -8 to 7. Let's deal with the easy one first, okay? The easy one is A, okay? This one is pretty easy, especially when you can use ternary operators. Because when you can use ternary operators, then you can say if x is less than 0, then this is a 1, otherwise it is a 0. Done. Is that making any sense? Sort of? Maybe not. Okay, think about this. In the original formula, okay, go back to the original here. In the other formula, in f itself, a is a quantity that you subtract. Okay, do you guys have any questions? Any questions I can answer? No. Okay. So you can see that this is the only part that can make a number negative. Even if D, C, and B are all 1s, this can still make it negative. Okay? So that means if x in the reverse function, if the value is negative, A has to be a 1. There's no other way. A got to be a 1 in order to make something negative. So that's why in the inverse function, the first part of the 4 tuple is really just saying if x is negative, I don't even need to look at anything else, just put a 1 here. And that's why I use a ternary operator, which is really handy in this case. What about B? B is really representing this bit here. Okay? Well, now here we have a little bit of a problem because to determine whether you have a 4 or not, you kind of have to flip things first a little bit, and then you'll work your way through. Is that okay so far? No? If I can use bitwise operator, it'll be easy. But since I cannot use bitwise operators, this gets a little bit more dicey. You can also use division and also remainder, as to help you out, and that helps a little bit too. Okay, so we'll go ahead and take a look at how to do this. So we're going to have to, every single case is going to be like this because we have to see whether the number is negative or not. If it is negative, I have to add 8 back to it in order for it to do something. Okay. So if it is negative, then we are dealing with 8 plus 8, and then we'll do something about it. If not, we'll just use x to deal with it. Okay. In fact, it's probably better to separate it on a separate line because it's going to get a little lengthy. All right. So when you look at this expression here, I'm flipping. This is basically taking the absolute value of whatever x is. Well, not the absolute value, but it's only D, C, and B matters in this case because I just took 8 out of consideration. Is that okay? Because if x is negative 8, then what I have to deal with here is just 0. If x is 1, 1, 1, 1, what I'm dealing with here is 1 with 7, which only has 0, 1, 1, 1 as a bit pattern. Are we still doing okay so far with this? Okay, so the trick to do this is to say, take this whole thing and use division, integer division, and divide it by 4.
If it's 1, 1, 1, 1, then it's negative 1, because 0, 1, 1, 1 would be 7.
Correct. Okay, so if x is negative 1, okay, so let's say this is negative 1. Negative 1 is less than 0, right? So that means I have to use this, which is negative 1 plus 8, which is 7. But 7 is the value of this entire expression. 7 divided by 4 is 1 because it's integer division. So this works for bit B. Okay. Are there any questions about this equation? I'm borrowing concepts from C in order to make this work. No questions about this one? What about the next one? What can you do about the next one? Now we know the next one is going to start with something like this because we have to take the sign into consideration first. But once we take the sign out, how do we get to the second least significant bit? You cannot just do a division anymore because if you just do a division, it's just not gonna work. So what do you have to do here?
I have to take the remainder when divide by 4 first.
Yep, take the remainder from the previous number and then divide this one by 2. That's right. Okay. So what you do is you divide it by 2, and I'm just using extra parentheses here to specify the operation, the order, and then you have to mod this one by, let's see, nope, divide it by 4 first, mod it by 2.
Mod 4.
Nope, mod this, sorry, and then divide this. There we go. And then the next one is going to be, you probably get the idea, right? The next one is actually not any more complex anymore. I'll just finish this, and then you guys can play with this when you have time, which is trivial. Because anything divided by 1 is that's something already, so the last operation is not needed. So it just be that. Is that okay? Well, the question is, yep, go ahead.
So how come you drop that 4 in
Drop
the
the
second
4?
formula when you go to the third one? So on top, you had that x plus 8, x mod 4 divided by 2, but the third equation you have there is like x plus 8 destination, the number is gonna change from step to step.
Right, because I just need to, okay, the last row, which is this part here, is to figure out how many ones do I have. Now, to figure out how many ones you have in a number is really just figuring out whether the number is an odd number or an even number. So when you divide a number by 2 and you have a remainder of 1, that means the least significant bit is going to be a 1. So that's how it works. Okay. So in the actual test, I'm not going to give you something like this nasty. I think this one is a little bit over the top, but it will be something kind of similar to this. Okay, so we have some. I mean, you can probably see how this one actually relates to computer science, because that's how we represent numbers, and that's partially why I chose this kind of question. Right, so we are running out of time. We do have one extra class before the exam. So if you study the practice exam and you have any questions about the practice exam, bring those questions on next Tuesday, because we are meeting on next Tuesday. So make sure that you bring those questions so we can talk about it.
Can you upload this video soon? Like, I think I'm gonna have to review this one pretty closely. I know I need to watch this video at least like 2 times.